guys, my name is Shiv. Welcome back to my channel called The Zytologist, where we talk about all things science related to home brewing and making beer. This is part 2 of my video in which I compared pressure fermentation to ambient fermentation. In part 1 of the video, if you haven't already checked that out, I went through the entire brew day, talked about the science behind pressure fermentation, and talked about the expected results that we would get in both of the cases. So this is part 2 where I have the results available with me. Both the beers have completed fermenting. The samples that I sent to the lab are back, so I do have the results of different chemical compounds, mostly esters and fusels, that we measured in both the cases for pressure fermentation and ambient fermentation. And I also have all the data we needed to study the kinetics of both the processes as well. So, well, here I have 2 glasses with me. I have 2 kegs with me. I'm gonna pour myself some beers and get onto tasting them and do a sensory analysis. But while I do that, I'll let you guys go and see what I had to say about the kinetic data that we obtained from both the fermentations.
Alright, so in order to compare the kinetics of both the fermentations, we need 2 sets of data. First is, of course, the specific gravity readings taken throughout the fermentation process, and the second is the timestamps or the respective times when those specific gravity readings were taken. So on the x-axis here, I have the timestamps or the time readings, and on the y-axis, I have the specific gravity readings. Now, for those of you who are familiar with using a tilt hydrometer, which is what we use in order to get the gravity readings for this experiment, you would know that the tilt hydrometer logs the specific gravity readings after a set interval to a spreadsheet, which then you can use to plot a graph such as this one. So usually when you're using a tilt hydrometer, you can set the interval after which you want the hydrometer to log the data. And if you have a small number for that interval, such as in my case, I think it's about every 10 to 15 seconds, a new reading is taken and then logged onto the spreadsheet, you get a fair amount of disturbance in the data. And that's just simply because of the little inaccuracies that are there in the tilt hydrometer, or some physical disturbances such as vigorous fermentation activity, so on and so forth. So, well, what I've done is I have gone ahead and processed the raw data that you get from the tilt hydrometer and removed all those disturbances, just to make the data look a bit cleaner so that we can analyze it better. Now, how I've done that is by, say for example, I have 20 different readings from a tilt hydrometer. Out of them, 15 of them say that the specific gravity is 1035, and the other readings say that the specific gravity is 1034 or 1033, for example. So I have overwritten the outlying data by the majority of the data in that set. So all the readings would read 1035. So after I've done that, I have obtained this graph here. So the blue line here represents the specific gravity curve, which is the change in specific gravity with respect to time throughout the fermentation. And the red line is the change in temperature with respect to time. So this particular plot is for ambient fermentation, as it says there for the name of the spreadsheet. So if you guys remember from the part 1 of this video, for ambient fermentation, we used 18 degrees Celsius as a fermentation temperature, which is probably the most liked temperature by USO5 yeast strain that we use in this experiment. And then towards the end of the fermentation, I increased the temperature by a couple points to 22 degrees Celsius. It should say Celsius there, I don't know why it says Fahrenheit. But anyway, I raised the temperature to 22 degrees Celsius to perform a diacetyl rest, just to clean up any of the VDKs that might have been produced during the initial stage of fermentation. So now let's look at the blue curve, which is our specific gravity curve. And the first thing to look at is the lag time that we got for the yeast. So the lag time is the time from when you pitch the yeast into the fermenter up until the time when fermentation actually starts, or when your yeast actually gets into action. So in this case, as you can see, I pitched the yeast at about 2:30 p.m. So 2:30 in the afternoon on 25th of February, and the fermentation started around 11:30 at night the next day. So we have a little over 24 hours of lag time. Just doing some quick math, I think that's about 30 31 hours of lag time. That amount of lag time is quite standard for any dry yeast. I think even on the Fermentis website, the typical lag time for USO5 that's stated is between 24 to 48 hours. So that reading is quite expected there. So once the fermentation started, we can see that the specific gravity decreased quite gradually over time till we reached our final gravity of 1014. The final gravity was reached on the 10th of March, and the fermentation started, or actually when I pitched the yeast was 25th of February. So the complete fermentation time, or the duration of fermentation in this case, is about 10 to 11 days altogether. This number is also quite typical, as those of us who have fermented with USO5 yeast before know that it takes about 10 to 14 days to reach complete attenuation. Now let's compare this to our pressure fermentation data. So for the pressure fermentation data, right off the bat, we can see that the lag time is visually much less as compared to ambient fermentation. So in this case, I also pitched the yeast at about 2:30 in the afternoon on 25th February, but fermentation started much earlier at about 2:30 at night that same day, so 26th of February. That's a lag time of about 12 hours, which is again much less as compared to our ambient fermentation. Now, the rate of change of the specific gravity with respect to time was also much quicker in this case, as we can see that our final gravity of 1014 was reached on the 4th of March. So now in this case, you would notice that the final gravity that we actually obtained was 1013, which is 1 point lower than our expected final gravity. Now, what I'm doing here is I'm giving it the benefit of doubt that the actual gravity was actually 1014 and not 13, because the amount of fermentables in the wort were accounted for, and I know that the final gravity should have been 1014, but sometimes the tilt hydrometer has some discrepancies in the reading and little inaccuracies, just because both the tilt hydrometers might not be calibrated exactly the same, and that's why it's reading 1013 here. But as I'm pretty certain that the final gravity should be 1014. Now, for pressure fermentation, if you remember from part 1 of this video, we fermented at a slightly higher temperature of 22 degrees Celsius, and that's one of the benefits of fermenting under pressure, that you can ferment at a slightly higher temperature and still get a clean flavor profile as you would with ambient fermentation. So in this case, I do not need a diastyle rest, just because under pressure fermentation, the VDKs are in theory produced already in lesser quantities and do not need to be reabsorbed. Now, if you wish, you can perform a diacetyl rest for pressure fermentation, but most of the times I've found that it is redundant when the VDKs in the first place are produced in much lesser quantities. Now, what I've done here is I have taken the data and replotted both our graphs on the same plot, just to make it easy for us to compare. So the red line is pressure fermentation and the blue one is ambient fermentation. As we can see that the lag time was reduced for pressure fermentation by more than half. That is 12 hours compared to about 30 to 31 hours for ambient fermentation. The rate of change of specific gravity with respect to time was also much quicker for pressure fermentation as compared to ambient fermentation. And then finally, the overall fermentation duration was also much less for our pressure fermentation as compared to ambient fermentation by a factor of about 5 to 6 days. So in conclusion, the data suggests that pressure fermentation is definitely the preferred option in terms of kinetics of fermentation, or how fast the fermentation occurs.
Alright, so pressure fermentation was clearly significantly quicker as compared to ambient fermentation, and makes for a better option when it comes to saving time. So if you don't like to wait for 10 to 14 days for your beer to ferment, you can definitely go for pressure fermentation and brew twice the amount of beer, or 2 different beers in the same time as you would a single beer. Well, that's all well and good, but at the end of the day, it comes down to how the beer actually tastes, and if pressure fermentation had any effect on the flavor profile of the beer, either in a positive or negative way. So I have both the beers poured here now. In fact, they've been sitting here for a little bit, and the head has dissipated slightly in both of them. Now, I do have the data for the different compounds, the esters and the fusels that we measured, but before I go into the data, I like to have a sensory analysis first, so taste the beers, and then read the data, just because I don't want the data to have an impact on how I perceive the flavors, and just have preconceived notions before I get into tasting them. At the end of the day, the beer is meant for your taste buds and how you perceive them, and the data is just meant to supplement supplement your opinion and calibrate your taste buds, so to say. So visually, I would say both the beers are quite identical. They're both quite clear in their appearance. Not much sedimentation either, just because I've bought these from the keg. The head on both of them has now dissipated slightly, but I had a healthy 2-finger head on these just a moment ago. So I've marked the glass with a letter P underneath for pressure fermentation and mixed them up, so I don't know which one's which. So this is completely a blind tasting. So without further ado, I am going to get a nose on this. It smells quite jammy, sort of like marmalade, and I think that's mostly because of Idaho hops. You get that sort of orange jam, citrus, slightly almost sweet smelling as well. Picking up a little bit of warmth almost, not in an off-putting way, but it's got some warmth to it. If I'll last it, maybe, I don't know, we'll figure it out. But yeah, it smells really fresh, smells pleasant. A little bit of honey as well. I'll get the nose on this one. Again, I'm getting that marmalade punch, really citrusy orange, like orange pith. Not as sweet smelling as the other one. Yeah, this one definitely smells a little bit warmer as compared to this one. But again, it's not in an off-putting way, just that I can notice it, but it's slightly warm in the nose when you take the aroma. Again, the aroma notes that we picked up follow through in the taste as well. It's quite jammy, marmalade, orange peel, orange pith, that sort of smooth bitterness. The sweetness is quite mellowed down in the taste. It smells sweeter than it tastes. Quite clean. I don't taste any sort of diacetyl or any butteriness, so to say. The esters, I would say, are also quite low. Just that little bit of warmth that I'm picking up, especially because I'm specifically looking for it, but otherwise I wouldn't be able to tell. Yeah, quite nice. Now let's taste this other one. cleaner tasting than the other one. I'm getting all those hop compounds, you know, the marmalade, the orange, that's pretty much the same in both of these. Well, we use the same hops. But in terms of the fermentation profile, it's cleaner. I don't taste any sort of warmth in this. No fusels that I can pick up. No VDKs, so no diacetyl at all. It almost smells a bit more crisp, if that makes sense, as compared to the other one. It smells like it's fresher. Yeah, overall I would say both the beers are pretty close to each other. There is not much difference at all. This one just tastes just a tad bit warmer as compared to the other one. And it was more so in the aroma as compared to the taste. It just smelled warmer rather than tasting that warm. But this one here is completely clean, as clean as it gets. Nothing wrong with it. Perfect tasting beer. So let's have a look of which one's which. This one is the ambient fermentation, and this one has a P at the bottom, so this is the pressure fermentation. Which one did I say was sweeter? Yeah, this one. So the ambient one is a little sweeter as well in the aroma, and the pressure fermentation not sweet at all. It's pretty crisp and fresher as compared to the other one. I believe it has to do maybe with some esters that this tastes slightly sweeter. Esters are in fact sweeter tasting compounds, but this one is much cleaner. More so now that I can see this is the pressure fermentation one, my mind's going, yeah, this is cleaner.
Now that we've tasted both the beers, now let's look at the data that we got from the lab and look how the different quantities of the esters compare for both pressure fermentation as well as ambient fermentation. So what I've done here is I've compiled all the different readings for different esters and fusel alcohols that we measured in the lab and put it in a neat table here for comparison. For the esters, we measured the concentration for ethyl acetate and propyl acetate, isobutyl acetate, isoamyl acetate, 2-phenyl ethyl acetate, ethyl hexanoate, and ethyl octanoate. And then for fusels, we measured the concentrations for isoamyl alcohol and 2-phenyl ethanol. So for all these esters and fusels, I have written down the usual human threshold, which is the value above which humans or human taste buds can perceive the flavor contributed by that specific compound. Then I've written down the typical range of the esters and fusels in which they are typically found in a wide variety of beer styles, all summarized together. And then finally, we have our measured concentrations of these esters and fusels in ambient fermentation as well as pressure fermentation. So all the numbers here are in terms of ppm, which is parts per million. So that's the unit that we've used there. If you are more familiar with moles or molarity, you should be able to quite easily convert it using an online converter, or if you know the formulas for the conversion. So let's get started with the esters. The first one is ethyl acetate. As you can see, the threshold is usually about 33 ppm and it's found in a range 8 to 48 ppm. In our ambient fermentation, we found that ethyl acetate was present at a concentration of 28 ppm, which is still lower than the threshold, so not that much of a problem. But in pressure fermentation, that was actually reduced to exactly half of the quantity that was produced in ambient, which is a considerable advantage if you are trying to minimize the production of this solvent-like tasting ester. The next one, in propyl acetate, the threshold is 30 ppm. Our labs currently do not have a typical range of N-propyl acetate, just because we haven't been able to find it in a large number of beers that we've tested, including commercial ones as well as the beers brewed at lab or for experiments like this one. But regardless, for ambient fermentation, we found 7.6 ppm in this specific sample. And for pressure fermentation, it's pretty much the same, just slightly reduced at 7.1 ppm. Isobutyl acetate was not found in either ambient or pressure fermentation, and that's mostly because the typical range for this ester is quite low. As you can see, it's from 0.03 to 0.25, and I believe USF5 strain does not produce, it's not a highly ester producing strain, so to say, so it most definitely did not produce any of those esters in either of the conditions, that is ambient or pressure fermentation. Then comes isoamyl acetate, the banana tasting ester. So the usual threshold is same in isoamyl acetate as for isobutyl, which is 1.6 ppm. The quantity found in ambient fermentation was 4.8 ppm, which is slightly above the threshold of 1.6, but still within the range that we usually find it in most beers. Considering this is a pale ale beer, isoamyl acetate probably does not have a place in this beer in that level of concentration, unless it is intended for your specific recipe. If you're doing, for example, a milkshake banana IPA or something, or a milkshake pale ale or something like that. But then in pressure fermentation, it was only reduced slightly by a few numbers to 3.6 ppm, but it's still higher than the flavor threshold of 1.6. Then comes 2-phenyl ethyl acetate, which is that floral or rose-like flavor contributor. So for 2-phenyl ethyl acetate, the typical range is also quite low. It's between 0.1 to 1.5 ppm. And I think USF5 again does not produce much of phenyl ethyl acetate, so we could not find any in either of the conditions. And then lastly, for ethyl hexanoate and ethyl octanoate, those esters are usually present in much smaller quantities as well. They were both detected in both the cases, in fact, but as you can see, the numbers stay pretty much unchanged for both the cases between pressure fermentation and ambient fermentation. Now comes the fusel alcohols. For fusel alcohols, we measure two kinds. First is isoamyl alcohol. Isoamyl alcohol, similar to isoamyl acetate, contributes a banana-like flavor, but also has that added warmth that you get from higher alcohols or fusel alcohols. So the threshold is 70 ppm for humans. The typical range it's found in is quite broad, between 25 to 123 ppm. In our ambient condition, we found 44.3 ppm, and in our pressure fermentation condition, it's pretty much the same at 44 ppm. Same goes for 2-phenyl ethanol, both at 11.2 and 11.1 ppm respectively. So in conclusion, we can say that the fusel alcohols were marginally affected or marginally reduced when we went from ambient fermentation to pressure fermentation. But for esters, in particular ethyl acetate, the reduction in ester production was considerable, while the other esters remained pretty much the same, with some marginal decrease here and there for a few esters. Now this is quite an advantage, because for pressure fermentation we fermented at a much higher temperature, so I would have expected the esters to be slightly higher than the ambient case. Even though we applied some external pressure, the temperature was still high, so I would expect some esters to be higher than the ambient fermentation, but that was clearly not the case, which is quite pleasant to see. So we get both the advantages in pressure fermentation, which is being able to ferment way faster as compared to ambient fermentation, as well as getting exactly the same, if not slightly better, or cleaner flavor profile as compared to ambient fermentation.
So there you have it. Not much difference at all in terms of the esters and fusels for both the beers. If in fact in pressure fermentation the ethyl acetate was actually reduced by quite a bit, and the other compounds stay pretty much consistent. So that was the warmth, I guess, that I was sensing in the ambient fermentation. But like I said, it was marginal and nothing off-putting, but still it was detectable. So I think that concludes the pressure fermentation experiment. In the end, I think pressure fermentation makes a great way to ferment beer at home, just because you get a quicker fermenting time and you get a cleaner flavor profile as well. It would be awesome to experiment further with different yeast strains, just because ES5 is quite a hardy yeast strain, which is quite clean and gives you a good beer regardless. It's quite hard to screw up fermentation using USO5, but I would be interested in doing the same experiment with different strains which are good at producing esters or phenols, for example, so like saison strains and maybe some quake yeast and so on and so forth. If you enjoyed this video, make sure you drop a like, you subscribe to my channel so you don't miss out any of the future videos in which I'll talk about all other things involved in brewing and the science behind it. Hope you learned something new from this video. You can leave a comment if you'd like to see me experiment more in pressure fermentation on any other ideas that you might have for experimenting in home brewing. Thank you so much for watching, and I'll see you next time.